little just plain old ordinary rectangle here, time, and I want to find the fluid amount of force being applied to it. Theoretically, I am thinking about the fact that I have a whole bunch of little rectangles drawn across this thing, which in this case, what do you notice about those rectangles? They're all the same in what way? They're all the same length. That length is never changing. So that's good news. Makes our lives easier here. When you go to set it up, you're going to use the same values of rho that you did last class. However, you do have at least one problem, maybe two today, that involves like oil or something else. And there is a chart on the side of page 492. It's in the middle of the fluid force page. It's down the left-hand margin. There's a chart showing you all the fluid forces of seawater, gasoline, machine oil. So if you need a different value for rho, there's a chart in there for you to use. So. Okay, so anybody's looking for it. So, alrighty. So in our case, we are doing normal feet though. This is normal water. What's rho if we're in feet? 62.4. See, you now have a new number to forever have memorized. Okay. What did H stand for? The depth. Okay. That is depth of each little rectangle we're talking about here. So we have to set up though, where's 0 at? If we're going the top of what? The top of the object or the top of the water? Okay. This is another one of those problems. You can do it either way. Over the years, I've discovered I have less issue if we make 0 at the top of our object. So it was a nice guess. But yeah, we are going to stick 0 is top of the object. So when I want to go talk about depth, x is my distance down to whatever rectangle I'm at the moment. That's x. So what's my actual total depth underneath the water? If I'm x down here, but I got to go clear to the whole height of the water, x plus 8. So your depth typically will be x plus something, unless it's right on the surface. So in this case, x plus 8 is my depth. Now, when I talk length, I'm talking length of the rectangle. In this case, is it changing? No, it's constant 8. So yes, we can just put a constant 8 in there. And then the width of the rectangles is always the x. All I need is something to integrate it between. And be careful. If this is 0 at the top of the object, I'm going 0 down how far? It's only, the object's only 3 feet deep, or it's only a size of 3 feet. So yeah, so it's just going to be 0 to 3. And yes, if you calculate an answer, it'll come out 9,734.4. What kind of units think you're doing just force? It's either pounds or newtons. And we were using feet, so yes, you got to be in pounds. So 9,734.4 pounds of force. So this summer when you lifeguards are sitting around the pool, you think about, this always used to bug me. I was always very afraid of the drain at the bottom of the pool, the big grate. I always thought it was going to suck me in. You can just think about how much force is being applied to that the deep depth. What is it, 10, 12 foot deep? 13 foot deep. Oh, that's right. So you have a high dive. So. All right. Why is this one going to be more pizzazzy? Yeah. But why is the triangle going to have more issue? Yes, our rectangles are changing now. That rectangle is going to be longer than the rectangle down farther. So that's going to make a big difference. And it just means we get to a little geometry. Once again, let me put the formula on here so that we have in this particular case, which rho value? It's 8 meters. So it's 9,810 newtons per cubic meter. Okay, what's the H stand for? Depth of the rectangle. So the X is the distance down to the rectangle. And so yes, this would be X plus 8 then. Then the fun part. How long are the rectangles? Are they a constant? Okay. They're changing. So this is screaming, I'm a similar triangle problem. So we know the whole thing is 8. You didn't hear it? Well, you should listen closer. What do I call the piece down here I'm trying to find? No, that can't be X. L, in this formula it's L. You can call it W if width makes more sense to you. I don't care. But technically with our formula it's the length of the rectangle, so they're going to call it L in this instance. If I have coming straight down then, I take that back. This is not 8 wide. I'm sorry. I'm listening to you, not paying attention. How wide? Yeah. This baby's only 3 wide. It's equilateral triangles with 3 meter sides. Where's X? Yeah. It's from the top down to the rectangle. So if that's X, what don't I know here that I kind of need? Do I know the height is 3 meters? No. This is an equilateral triangle. The sides are 3 meters, but that's not the height. So do we know the height? That is exact dead center, yes. Yes. If you cut it in half, we need to know the actual height of the whole thing. And I know then that's 1.5 and 3, and I would like to think at this point, yes, thank you, we can do the Pythagorean theorem. Are you willing to trust me and have me tell you that it comes out 2.6? Okay. If you do Pythagorean theorem, if you 3 squared minus 1.5 squared, you will get 2.6. So our whole height here is actually, whoops, that to move out of the way. Oh great, now I really messed it up. Over there. So that's really 2.6. Oh, sorry, yeah, it's kind of messed up there. I'll fix for you. So now I need to know which parts of these two similar triangles. I have to know the length of the large triangle, length of the smaller triangle. I've got 3 across and I've got L across, so I'm good on those. What else do I need to know to do? I need to know the depth of how tall the entire big triangle is, and I have to know the depth of the little triangle. Where is the little triangle I'm looking at? Is it X? It's X, so I need the bottom piece down here, which is going to be 2.6 is the total height, so that's going to be 2.6 minus X. That length in there. I guess I could color code it. So now how do I solve for L? She just said L over 3. So she did small triangle width to large triangle width. And so then we need small triangle height, which is 2.6 minus X, to what? To the whole height. Okay, why was it good that she started with L? Now we just have to multiply 3 over, and I wouldn't bother to divide it out. I would literally just leave this as 3 divided by 2.6 times the 2.6 minus X. Just let those constant numbers be a fraction out front. Don't bother to crunch all the numbers. Your calculator will do it once you put it in the integration. I said I was taking them away the next chapter. This is the chapter where they prove their greatest use. Because integrating some of these by hand isn't worth the time it takes when we do have technology. What am I missing? where I'm going to integrate between. Okay. Because my object is starting, height, the top of the object is 0 up here, so how far down am I going? 2.6. And you'll get a lovely answer of 339,230 what? Newtons, yes. We're in straight force. We're in the metric system, so we are Newtons. Several after-school tutors who get requested because they tutor math. See, there's always that slight bit of joy in terrorizing them. Whoa, I went too far. Back. All right. Okay, last one. Why is this one nice? It does top the water. Why is this one mean? It's a semicircle, and they are the biggest pain by far.
Is this the last one?
This, yes, is the last one.
3 minutes.
I will never make it in 3 minutes. We're stopping now.
Bye, Dylan.